All right, good afternoon. Okay, so let's start lecture. Okay. We'll continue on the topic at here. So if you recall, in the previous lecture, we looked at how to get a discretized state space equation. And the previous lecture we talked about the concept called transition matrix. It's a matrix basically phi equal to a to the power of k. Okay, and that transition matrix was defined from the solution of this discrete system. And we showed that in order to calculate this transition matrix a to the power of k, we have the first method here, which is essentially taking z inverse z transform of this expression. So that's the first method. So how we can basically calculate this a to the power of k transition matrix. And the second method is basically what we're saying is if somehow we can diagonalize this A matrix, so basically into a AW matrix. The diagonal elements of this AW matrix are the eigenvalues of the A matrix. Okay, if somehow we can diagonalize into this one here, right? And of course the A and AW, okay, are related by certain relationship, for example P inverse. Okay, so this is how A and AW will be related, and then we can calculate this a to k to the power of k becomes P AW to the power of k and then P inverse. Okay. So that's the second approach that we look at it. So from here to here I showed you, essentially if you can write this one here, if this is diagonal matrix and this is the results for a to the power of k. And for diagonal matrix to the power of k, and it's very simple, just all the elements to the power of k. Okay. So this is basically, now we're looking at is how can we basically diagonalize the A to AW, and what will be this matrix P at here, and that's the topic today, which is the similarity transformation. Okay. So the concept here is similarity transformation. So let's define this concept first. Okay, so let's look at the definition first. Okay. Given, I'll use two matrices at here to illustrate. Given two square matrix, okay, n by n matrix, then A is said to be similar, okay, to B. Okay, so A is said to be similar to B if there is a non-singular matrix P such that P inverse A times P equal to B. Okay, so here's the concept of similarity here. So we'll look at it. So this is a pure mathematical definition here, right? Okay. So basically, the A and the B was connected with this relationship right here, and the P matrix. Make sure this is a non-singular matrix, which means the determinant of the P matrix is not 0. Okay, And then for this one here, sometimes we can also denote. So it can also be denoted by A tilde B. So mathematically, if the two matrices are denoted with tilde sign in between, then they basically means they're similar. Okay? Yeah. This is a similar here. There are a few comments or few properties associated with this similarity. The first one here is called, it's a reflexive property. So reflexive property basically means is any matrix, okay, is similar to itself. So it's like you look into the mirror, right? That's similar to itself. Okay. You can actually write this one here into the same format as a definition. So if you use the identity matrix, right? So that's in the same format as the definition. So this is basically A similar to self, or it's reflexive. Okay. Another property is called symmetric. Okay. Symmetric here. Symmetric basically means if A is similar to B, so if A is similar to B, then B is also similar to A. Okay. So that's symmetric property. And this is actually quite easy to prove at here. So I'll show you. Let's say if A is similar to B, basically means according to the definition, we have such type of relationship, right? Yeah. Now if I multiply a P matrix here and P inverse matrix at here, so essentially this formula here will become A equal to P times B times P inverse. Okay? Yeah. Right. So here's B at here, then you have P at here, P inverse here. Okay. So move the P matrix to the other side. Right. So then you get A equal to this. So this is basically same format as the definition of the similarity, right?
But
yeah.
Backwards?
Well,
the P inverse is after the E.
Yeah.
Top P inverse is before the A.
Yeah. So okay, let me just Okay, so P inverse AP equal to B, right? Yeah. So how do I move all the P inverse to the other side, right? So you basically what you can do first, multiply P inverse here, P inverse here. Yeah. And then multiply P at here, P at here, right? Yeah. So this becomes I, this becomes I, then you get this, right? Yeah. Good. So that's symmetric property. And then another one is called the transitive property. Okay, transitive. This one essentially means if A is similar to B and B is similar to C, then we can see that A is similar to C. Okay, so that's the transitive property. Okay, yeah. And this is also quite easy to prove. So let's say we start with A similar to B. That means P inverse AP is B. B is similar to C. That means you can find a Q matrix. Okay, and then Q inverse BQ equal to C. Cool. Yeah. So based on these two relationship, so I can substitute this one here into here, right? Yeah. So then what we get is you got a Q inverse times P inverse times A, and then P times Q equal to C, right? Yeah. Yes.
In that last one, is it considered that A, B, and C are transitive, or like B is transitive, or how do you describe that property?
This one here?
Yeah.
So basically given A similar to B and B similar to C, then we can conclude that A is similar to C. Yeah. So it's like a sequencing, right? You know, from here to here, and you end up the next one. Yeah. Q inverse P inverse is equal to PQ inverse. Okay, and then times A, and put this PQ together. So you see now this is exactly in the format of the similarity definition, right? Yeah. So that's why A is similar to C. Okay. Yeah. So that's the basics behind this concept of similarity transformation. Okay. So this actually explains quite a bit in terms of deriving a state-space model for a certain given system. So if you recall that, right? If you recall when we derived the discrete state-space model, and we showed quite a different, basically different formats, right? We showed what? Control, canonical, and we also have observable canonical, and we also have diagonal, right? Yeah. So, and there are definitely a few more other different formats here. Okay. So you can, for example, if we denote each one of these form using the matrix A1, A2, A3, right? So different form has a different matrix. So now you can see now using the similarity transformation concept. So what we can see is, if you start with A1, you can somehow find appropriate matrix P or whatever matrix, non-singular matrix. We can transform that into A2. We can transform that into A3, and A3 can transform back to this A1, right? So all of this, you can use this this so-called similarity transformation. Right. So this similarity transformation concept basically explains the phenomenon why you would have an infinite type of state space model, right, for the same system. So literally, you can transform it to any kind of a matrix, right? Yeah. So that's the point of similarity. But of course, we're not going to look at everything there. So we only look at kind of some of we'll look at the next one, basically the diagonalization of this matrix A here, right? That's the objective, because we wanted to diagonalize the A into AW, okay, and also find the P matrix, appropriate P matrix there. Okay, so the next topic here, basically, now let's look at the diagonalization. Of this matrix A, okay. Objective, okay, very simple. The objective is to develop a useful factorization and A equal to P AW P1, so A equal to this one here, and in this expression, of course, the A matrix, original A matrix, needs to be a n by n square matrix. Okay. So once we find this one, then we can use this formula to calculate A to the power of k, right? And AW at here, okay, as we said, is the diagonal. It's the diagonal matrix. That's a simple objective. Okay? Yeah. And I'll give you essentially 3 different theorems here as a guideline of how can matrix A be diagonalized. Okay, so let's start with the first theory. Okay, the first theorem. This is more or less like a pure linear algebra type of concept. Okay, yeah. First theorem, basically, this is what it says. A n by n matrix. Okay. Well, this is, what do you see? A n by n matrix A. This is a different meaning, huh? This is a matrix A here, with n distinct eigenvalues. Maybe I should, let's put this way, if, okay, if a n by n matrix A, okay, has n distinct eigenvalues, then this matrix A is diagonalizable. Okay, so that's the first theory. So it answers under what type of condition that this matrix can be diagonalized, right, into a diagonal matrix. Okay, yeah. If this one has n distinct eigenvalues, then this will be diagonalizable. We're not gonna prove it here. Okay, so just the theory. But this theory here, just note it here. Okay. This is if then. So this theory is essentially just a sufficient condition. Okay. This is sufficient condition, not a necessary condition. So sufficient condition means you could see if A then B, right? But it's not true that basically, let's say A is diagonalizable, then A must have n distinct eigenvalues, right? That's basically what it means. That's right. Yeah. If and only if there'll be both sufficient and necessary condition. Okay. So let's look at this under the first theorem and here, and let's look at how we can diagonalize the matrix here. Okay. Again, we're gonna have to recall a little bit linear algebra concept here. So recall that. Okay. We're gonna let Zi, okay, be the eigenvalues. Okay. So we're gonna let Zi be the eigenvalues of matrix A. So whenever you're given a matrix, and you can always calculate its eigenvalue. Well, if that's an apple, then you better throw it away. So if Zi be an eigenvalues of matrix A, then how do we calculate this Zi, right? If you recall that, basically we can use Zi minus A. Okay? I is a unit matrix. Then you calculate the determinant, and then you can get this Zi here, right? Yeah, this is how you can get the eigenvalues. And eigenvalues, the I here. Okay. Now remember this. This is a case we're talking about distinct eigenvalues. So if A is n by n matrix, then you're gonna have n number of eigenvalues, right? Yeah. So for each eigenvalue, right? For each eigenvalue, you learn linear algebra, there is a eigenvector associated with that eigenvalue, right? So let's let this pi be the eigenvector. Okay. Corresponding to Zi. So each eigenvalue has a eigenvector, right? Yeah. And then the eigenvalue, eigenvector, and the matrix A are connected with A times pi equal to zi times pi. So small p, okay? Yeah, small pi. Right, that's the connection between the eigenvalue, eigenvector, and the matrix A, right? And the eigenvector pi, it's a vector, of course. It's basically the ith vector. Then the vector is n by 1 vector, so you can write down the components. This is just the first p1i, let's say p2i, and then p, and then keep going down until pni. So that's the structure here. So, and if you recall in linear algebra, this is a very unique relationship actually. What's so unique is because, so when you use a matrix A time a vector, right? So for example, you have a matrix A, and then you time a vector x, and you get you time a vector x, and you get another vector b, right? Yeah. So if this x, let's say maybe is 1, 2, 1, then you get a b, I don't know, maybe it's 3, 4, 5, right? Like that. Okay. So then what happens is basically the A matrix that is here is serving as a sort of a transformation, right? You use this transformation, you use the matrix A time this current vector, then you get a different vector, right? Yeah. And what happens is this x used to be pointing, let's say this way, okay? This is x here. And then after calculation, the transformation, your b goes this way now. Right, so that's the idea. Basically, when you use an A times vector and then generate another vector, right? Yeah. Now the eigenvalue, eigenvector. Now you look at this one here. So A times the eigenvector, right, generates another vector, which is this one, right? But this vector here, and compared to the original eigenvector, is what?
Just scale.
Yeah, just a scale difference, right? It's in the point to the same direction, though, right? Yeah. So that's the difference, right, for this eigenvector and eigenvalue at here. Okay, yeah. If you learn robotics, you know there'll be more about this rotation here, this transformation, right? So that's the point of this here. But you know we're not we're going to using this the results that are here for our purpose of a diagonalization at here. Okay, yeah. Diagonalization, if you go back to our objective, remember is to find the p at here. Because AW is the diagonal matrix, and AW is basically diagonal matrix with its element, right, as the eigenvalues at here. So let me erase this part here, okay? I don't need this. So let's define basically what that matrix P is, okay? So I will show you why this is, but let's write it down first. Let's define this transformation matrix P, okay, as this one. So capital P equal to P1, P2, and Pn. So this is how we define that transformation matrix P. And this P is also a n by n matrix at here. Okay, so let's take a look at this P at here. Okay, so what this P is basically contains 1, 2 until n. So it contains n number of columns, right? And each column is one of this eigen vector here. So that's what this P is. Each column is n by 1, then together you have an n by n, right, matrix. So that's the P. If we define the P like this, then we can see now basically the AW, okay, is actually basically equal to P inverse A times P, and which basically means the AW, right, you have a Z1 at here, and Z2 up to Zn, and all of the off diagonal elements are 0. So that P matrix is exactly what we're looking for. Okay? If we can define a P like this, then we can diagonalize this A matrix into this diagonal format. Is that good? Yeah. So here's a very simple proof of this one here. Okay, simple proof. So what we're trying to prove is we're trying to show. So basically, we're trying to show this AW equal to P inverse AP. Okay, this is what we're trying to show. Is that good? Yeah. Now, trying to show this is equivalent to if I multiply both sides by P, okay, then this is basically equivalent to say, instead of showing this, I can try to show this, right? So I don't need to show this. If I can show this one here, and then I basically proved the original one. Okay. So let's try to show this one here. Let's try to see if we can show that P times AW is the same as A times P, right? So let's take a look at what P times AW is, and also what A times P is, right? So let's look at A times P first. So A times P equal to what? So A times P, this is A at here, and P matrix is the matrix that defines the transformation matrix. So let's write it down here: P1, P2, and then Pn. Okay. So we can multiply the A into each one of the elements, which is still a vector here, right? So multiply A into the bracket. So you got A times P1, A times P2, and A times Pn. Okay? Yeah. So you look at it, you got to make sure the dimensions are okay, right? Dimensions are okay. So as we said, basically each one of these here are just column vectors. So each one of these are column vectors. So A is n by n times n by 1, you got n by 1, right? So each one of these right here is still an n by 1 column vector here. Okay? So altogether you got this n by n matrix, right? N by n matrix. Okay? And individually it's n by 1. Let's say that's what A times P is, right? That's A times P. So let's look at what the P times AW. So P times AW. And P is still the same matrix, so P1, P2, and Pn times AW. AW is a diagonal matrix, so here's Z1, Z2, and up to Zn. Okay, that's P times AW. Right. So now let's multiply the matrix that is here. So when you multiply this matrix with this is the matrix here, right? This is the matrix. So this is column, column, column here, right? When you multiply this with that matrix that is here, so if you can imagine this, you basically get what is it? So each row, right, times the column here, right? Each row times each column. So you get P1, this whole row right here times this, and this row here times another one here. Okay, that makes sense, right? So, but for each column here, this is all 0 here, right? And then this is 0, and then that's 0 here. So this first row times this column here end up with what? Z1 times P1, right? And then this row times the second column here end up with Z2 times P2. And they keep going until the end. You got a Zn times Pn. Okay. Yeah. So now, if you compare this AP and PAW right here, this element and this element, they're the same, right? That's basically what connects the eigenvalue, eigenvector, and the original matrix P. So that's why this AP equal to PAW, and of course we got A here equal to P times AW P inverse. Okay. Yeah. So that proved that the choice of the capital P matrix, okay, which has column vectors as the which has the eigenvectors as the column vectors, right, will give us this diagonal matrix AW. Okay, so that's the transformation matrix P here. Okay. So let's take a look at an example here. Here's a matrix A, and this example I believe the same as what we did in the previous lecture here. Okay. So if this is A here, and then we want to ask for what is A to the power of K. Okay. Yeah. I mean, you can choose A to the power of K as in the previous lecture. Choose that formula to calculate A to the power of K here, right? But I'm going to choose the similarity transformation approach. So first step, right, get the eigenvalue of A. And it's quite simple. You basically let Zi minus A equal to 0, and you get a Z1 equal to -1, and Z2 equal to -2. So we have two distinct eigenvalues. Okay. Then the next step is basically what is the eigenvector associated with P1, and what is the eigenvector associated with Z2. So we need to find the two eigenvectors here, and once we find the two eigenvectors, then we can construct the similarity transformation matrix P. Right. Okay. To find eigenvalue and eigenvector, so let's start with the Z1 first. Let's start with this one. So you start with the formula A times P1 equal to Z1 times P1. Right. So start with this one, and this is essentially the same as Z1 P1 minus A P1 equal to 0, right? Yeah, move everything to the one side. Or it's Z1 I minus A times P1 equal to 0. Okay, yeah. P1 is what we're looking for, because we know Z1 is equal to -1, so we're looking for the P1 here. So let's let P1 equal to, there are two elements, right? Let's let equal to P11 and P21. Okay. Let's let the P1 equal to these two elements. And now we're going to substitute everything into this formula here, this expression here. So Z1 is -1, so -1, 0, 0, -1, right, times I, minus A, and A is 0, 1, -2, -3, times P1, so which has, let's say, P11 and P21 equal to 0. Okay, yeah. Simplification, right? Simplifying this right here, and you end up with a -1, -1, -2, -2, and then times P11, P21 equal to 0. Okay, so far so good? Yeah. Now multiply this row with this column, multiply this row with this column, but these two here are essentially the same, right? You know, just the scale difference. So you could just write down one expression. So from here, you end up with just one expression: P11 plus P21 equal to 0, right? Just one expression. Yes. Sorry, which one? Here? Oh, okay. Just a sec here. Negative 1. Oh, yeah, you're right. Yeah, positive 2 here. Good. Thank you. Excellent. So that's still the same, right? Yeah, this one's still okay. Yeah. So one expression, infinite number solutions, right? Yeah. Which makes sense because why? See, this is a vector basically, right? This is a vector. And when you have a vector, what does that mean? You can multiply the same vector with any scale, then you get a different vector, but the same direction, just different scale, right? So for eigenvector, you can have infinite number solutions, right? You know, basically all have a different scale. Okay. So here, to simplify, often in time, you pick the simplest solution you can get. So what we can do is we can see, let's let P11 equal to 1, and then P21 equal to -1, right? And these two add together equal to 0, right? Yeah. So that gives us this P1 vector, which is 1, -1, and here. Okay. Yes.
Previously, in the equation, you put that A times the eigenvector is equal to, like a scalar. I don't think it's on. Oh yeah, right there. A scalar times the eigenvector itself. Isn't that scaling value an eigenvalue of it, or is it? Yeah, to the left, just to the left again. Yeah, there. Is that any scalar, or is that an eigenvalue?
This is eigenvalue.
So is there still an infinite number of solutions for that?
Oh, this cannot be. No, this has to be eigenvalue.
Okay.
This cannot be arbitrary other scales. Right? So if you think about it, you cannot claim basically A times P1 yield a vector with the same direction as P1, but arbitrary other scales.
You could keep scaling that afterwards and get.
Right, you can keep scaling the P1, no problem. Right? Yeah.
Okay, makes sense.
Yeah. So basically, let's see if I multiply a 2 at here, right? That doesn't change the expression here. Yeah. Very good. Yeah. So P1, I pick this, and often in time, if you use MATLAB will generate actually a normalized P1. So it basically will divide it by √2. Okay. Yeah. So that actually it's not very not that good from a calculation point of view, because you divide by √2, it doesn't give you divided by √2. What it gives you is 0.707 here, and then -0.707, right? And if you have no idea what 0.707 is, then you don't know what this is, basically, right? Yeah. Okay, so that's P1. So then you can similarly calculate the P2. P2 will be try to exercise yourself. P2 will be 1 over -2. So if you choose MATLAB, there's a command called EIG, and if you feed this command with the matrix A, and then you can let it return 2 parameters. One is eigenvalue, and the other is the eigenvector. Yeah. So the D at here, right? The D at here. Oops. The D at here, what it returns is basically it gives you a matrix. There are 2 columns at here. Okay, there are 2 columns. The first column basically is the P1, and the second column here is a P2. Okay. So you got to interpret that appropriately, the results here from the math lab. Okay, and see it here basically is the Z1 and Z2. Okay, yeah. Okay, so now let's put these results together, right? We put the results together. Basically, we construct that P matrix with the two eigenvectors. So we plug in the value here. So 1, -1 is the first column, and then 1, -2 is the second column. So that gives us the transformation matrix P. And of course the D matrix, not the D matrix. Oh gosh. And then that AW matrix, right, has -1 here, -2 here, 0, 0. Okay. And you can easily show that this A matrix is the same as P times AW, P inverse. So, and you can show this, okay? Easily you can get that. And once you get this, and then we're looking for A to the power of K, right? A to the power of K. So A to the power of K, because the similarity transformation here, so that's basically a P times AW to the power of K, then times P inverse. Okay. And P matrix already have it over here, so 1, 1, -1, -2. And AW here is -1 to the power of K, 0, 0, -2 to the power of K. And then P inverse, you can calculate your P inverse. So it's a 2 by 2 matrix, and you can calculate the inverse easily, right? So this matrix multiplication is not too bad, right? Yeah. Then you can get the results, which will be the same results, right, as we did in the previous lecture. Okay? Yeah. So try it. So that's the idea for this diagonalization. That's based on the first theory, the theory number 1, which says A has n number of distinct eigenvalues. Okay? Yeah. All right. So let's take a look. Let's take a look at the second theorem, and then I'll show you something else to the second theorem. So second theorem basically essentially it gives us a different perspective in terms of diagonalization. For this matrix to be So for this matrix to be diagonalizable, okay, the condition is if and only if A has n linear independent eigenvectors. Okay. So for this guy to be diagonalizable, then if and only if and only if A has n linear independent eigenvectors. So this is slightly different. This is actually different from the other theory here, right? But the other theory, if you look at P1, P2, and they're basically linear independent, right? Yeah. Now this one here, as we just said, this one here, this is what? Both a necessary and a sufficient condition. Okay? Yeah. So let's take a look at the details here. First of all, what does n linear independent eigenvector means, right? So let's say you have, if n is n by n matrix, then we gotta have basically P1, P2, and then up to Pn number of eigenvectors. Okay, so we can have n number of eigenvectors here. For all of the eigenvectors to be linear independent, now if you recall that, essentially if you multiply each one of the eigenvector with a constant k1 to kn, and then if you add all of them up, okay, and let it equal to 0. So basically, let's say if we let this guy to be 0, right? Yeah. The linear independent, let's call it Li at here. So for Li, right? If the only solution, right? So this is basically an equation. If the only solution is k1 equal to k2 equal to up to kn equal to 0. Okay. So if you write down this equation right here, and then you try to solve for k1 to kn, and you find out that the only solution, right, to be 0 is all of the coefficient to be 0. If that's the case, then we can see this P1, P2, and up to Pn, and they are linear independent. Okay, right. So essentially, they are not related, right? So you cannot express, you cannot obtain one of the eigenvector based on a certain combination of other eigenvectors, right? That's basically what the linear independent basically means, right? Yeah, yeah. So there's no relationship, right? You know, if you have a mom and dad, and you know, you can somehow you can, right, relate it to the kids. But this one here, completely unrelated, right? Yeah, that's linear independent. So let's take a look at this case study here, right? And let's take a look at this example here with this condition, how we can basically construct or how we can diagonalize the A here. So let's start with the A matrix at here. Given a matrix, okay, given this A matrix, let's first solve for the eigenvalues. Okay, so set equal to 0, solve for eigenvalue. Now, if you let equal to 0, you look at the determinant. It is, okay, it's this relationship. So z minus 2 to the power 2 multiplied by z minus 1. And what does this tell us? Basically means it has how many eigenvalues does this A matrix have? 3. So there's z equal to 1 for sure, right? And there's another one which is z equal to 2, but this one repeat twice, right? Repeat twice. So this is a repeated one here. Yeah. So technically speaking, it has only 2 eigenvalues, right? 2 eigenvalues, but one of the eigenvalues repeated twice. Okay. Yeah. Now this is essentially, if you look at this solution here, that doesn't fall into the first theory, right? So it doesn't have any number of distinct eigenvalues. Okay. Then you cannot just conclude immediately, right? You cannot conclude immediately saying, okay, so A is not diagonalizable, right? You cannot conclude that. So what we have to do is, let's take a look at the eigenvectors associated with each one of these eigenvalues at here. Okay. Yeah. So for z1 equal to 1, so I'm going to skip some detail. You can try yourself. You will find that the eigenvector, okay, associated with this z1. Okay, a candidate to p1 is 0, -1, 1. Okay, so that's one candidate eigenvector. Yeah. If we look at the z2 equal to 2, and we'll be able to find two eigenvectors. Okay, we'll be able to find two eigenvectors, and I want you to try to the exercise yourself right here. So this step, just see if you can find this p2, this is p3. Okay. So there are two eigenvectors associated with this one eigenvalue. So now let's look at each one of the eigenvectors that are here, right? Each one of the eigenvectors, whether they are linear independent or not. You can use alpha to help you, but this is obviously a linear independent case. So then we can construct that P matrix with the first column of P1, second column P2, and third column P3, so which is 0, -1, 1, 0, 1, 0, -1, 0, 1. So that gives us this similarity transformation matrix P. Okay. Good. So yes.
So those columns, once you find vectors, can you put those in any order?
Can you put it any order? Yes, you can. Yes, you can. But if you put it any order, so if I put it this order here, right? Then if I do this, if I do P inverse AP, guess what do we have? We get 1, 2, 2 at here. Okay, right? So this one here corresponding to this eigenvector, and this 2, 2 corresponding to this 2, right? So if you switch this order here, then you will switch this one here.
But
Yeah.
Still
Huh?
but it's still correct.
Yeah, still correct. Yeah. Yeah. Good. Okay. So that's the second theorem, right? The second theorem here. Now there's another theorem here. Okay. We're not going to give you any extra. I'll just write down the theorem here. Okay. This is basically sometimes can come in handy here. If A matrix is a real symmetric matrix, okay, if A matrix is a real symmetric, then the A matrix must have n distinct real eigenvalues. Okay. So that's a third theorem. And this one comes very handy. Actually, later when we learn a common filter, I think, yeah. Then often in time, this real symmetric matrix is a very common matrix in control design. So what this basically, you can always use this conclusion. If this is a real symmetric, then A must have n distinct real eigenvalues. If A has n distinct real eigenvalues, guess what? Then A matrix can be diagonalized, right? Yeah. So that's theory can come into handy.
What does symmetric mean? Is that
Symmetric meaning, let's see, for example, A equal to, let's see, for example, right? Let's see, 1, 3, 4 here. Doesn't matter. Huh? Then you got a, let's say, 2, 5. Then this is 2. This is 5. This is 6. This is 6 here. That's symmetric, right? Yeah. Or in other words, the A equal to A what? That's right. Okay. Yeah. Okay. So essentially, the three theorems are good enough for doing this similarity transformation, right? Yeah. So one little concept here to tie up the loose end in here. Okay. Yeah. Now you can establish concept. I can use a similarity transformation to transform the original matrix A into any other different type of formats, right? Not necessarily a diagonal form. Okay, not necessarily diagonal form. So what does that mean, basically, to our state space equation here, right? So let's say I'll start from original. So here is the original given state equation, state space equation. Okay. So now I'm gonna apply the similarity transformation now, right? So I'm gonna apply similarity transformation. Yeah. Here's what we're gonna do. So let's see, we're gonna choose a transformation matrix P. Okay, so I choose transformation matrix P. Okay. So I'm going to apply this transformation matrix, okay, to this original state vector x of k. So apply P inverse to x of k. Okay. So the writing in here is just for the ease of writing in the future. So you could say just P inverse here and P and here, but that's okay. So which means what? I apply P inverse to x of k. So this is a matrix, right? It's in by main matrix. Inverse is still in by main matrix. Okay. Then we got a different vector, right? We got a different vector. Let's call it wk. Okay. So you choose arbitrary, right? Not necessarily arbitrary, but you could choose any transformation matrix P, and you inverse that. Then you apply this P inverse to x of k. Then you get a completely different set of state vectors, right? Yeah. So here is your original state vector. Here is another state vector, right? So these two, okay, will all look like different now, right? And this one basically means your x of k is equal to P times wk. P times wk. Okay, so now let's take a look at what does this transformation bring to this original state equation here. Okay, so let's take a look. So x here, so this one here will become P times w of k plus 1. And then a times pw of k. And then b times u of k, no change, right? So if you substitute x of k with pw into the original state equation, we get this, right? We get this. And your y of k is equal to c times p w of k, right? Okay. And then a little bit change manipulation to the first equation here. So what we can do is we can multiply P inverse on both sides of this equation here. Okay. So we get P inverse times C is unit matrix. So here P inverse AP WK plus P inverse B U of K. And Y of K equal to, let's call it, still call it CP here, that's okay. Right? Okay, so see now, with this simple manipulation, the original state space model, okay, equation is transformed into a completely different state space model now, right? Yeah. So for this state model, you have a state vector which is W of k. And then the system matrix at here. So this one here, we can call it, I don't know, let's call it, yeah. Huh? A prime, sure, yeah. In this one, let's call it B prime, and this one, we can call it C prime, right? Yeah, good. So this is basically a new state equation, right? New state equation. If you choose your P appropriately, then of course your A prime could be what? Could be that diagonal matrix, right? Yeah. So, and this essentially tells you, you can have infinite state model here. But what's the connection, right? What's the connection here? Just a few comments. Okay, a few comments here. If you look at the calculation of the eigen values, okay, for both A and A prime. So if you look at the calculation eigenvalues, so both will have the same eigenvalues, right? So that makes sense because you're talking about the same system, right? Yeah, you're not changing the system here. You're just describing the system differently. Okay. And you can actually show this. You can actually prove this quite easily at here. So a very simple proof at here. Just to give it to you. Let's start from Zi minus A prime. Okay, let's start from here, and we know that the A prime is P inverse AP. Okay, so right, A prime is P inverse AP. Okay, and then this manipulation, this Z times unity matrix, I'm gonna use P inverse IP, so no change. So P inverse IP still I, right? Yeah. Then P inverse AP. Okay. So then you have a P inverse P at here. So this one can be rewritten as P inverse on the outside, and the Zi minus A in the middle, and then outside here is another P matrix here. Both of these are constant, they're non-zero, and this is the only one that you can solve with the variable here, right? So that gives you this Zi minus A equal to 0. So yeah, I mean, you can cancel this basically. It's like a 2 times x equal to 0, right? Then, or 2 times x minus 2 equal to 0. So the only solution is x minus 2 equal to 0, right? So that constant is gone. Yeah. So that shows you the idea, even though they have a different system matrices, but the eigenvalues are the same. Okay. And the other one property is, if you look at the determinant, of this, not AW, determinant of A prime and the determinant of A, okay. So if A prime is a diagonal matrix, then its determinant is what? It's the multiplication of each one of the eigenvalues, right? The diagonal elements. Right. So let's say if you have a matrix 1, 2, 3, n. What's the determinant? So 1 times 2 times 3 times n. Okay. Yeah. And of course, here A prime A doesn't necessarily is a diagonal matrix. However, when you look at the determinant of this, they are all equal to Z1 times Z2 and then times Zn, that kind of things. Okay.
So yeah. It's not negative. That's not negative.
Oh, this is not negative. So this is just my silly.
I figured. I just want to make sure.
What should I use? Plus? No.
No, it's okay. It's just in that situation.
Yeah. Good. So that's another property. And also you can look at the trace. Trace basically means is you add up all the diagonal elements. Okay, so you have a diagonal elements. If you add up, summing up all the diagonal elements up, and you'll see that for all the similarity transformation, the trace A prime is the same as the trace A at here. Okay, yeah. And last one, if we're going to derive back to the original pulse transfer function. So if you recall, the formula is if it's right, it's this one here. So you can re-derive or reverse to the original pulse transfer function. So of course, you're talking about the same system, then then you can get the same results if you use this C prime, A prime, B prime, and C prime. Okay.
Because it has the same eigenvalue.
Exactly, because they are talking about the same system, right? Yeah. So your pulse transfer function cannot look differently, right? It's only one form. Yeah.
Is it supposed to be inverse?
Oh yeah, inverse. Yes. Thank you. Okay. So yeah, that's pretty much for this part right here. Okay, for the similarity transformation. Yeah. Any questions? All good. Okay. Yeah. So we have a little bit of time here. I'm going to actually stop a little bit early today. I have to run over the other side from a midterm. But I'll start the topic here. Let's see how far we can go. Okay. Yeah. The next topic is basically on controllability. Okay, and observability. So this is a very similar topic now. If you're in a modern control system, okay, yeah. But of course, we're talking about controllability and observability for a discrete state space model. So let's start with the ideas. What's controllability and what's observability, basically. Okay, let's look at controllability first. Given still the same system, let's say we have a state space model at here. Okay. Now I'm gonna from here somehow, if you probably will notice too, I'm gonna change my notation slightly for the state model. Instead of using A now, I'll use a G now. Okay. And there's a bit of slight change modification in the lecture notes too. Okay. Yeah.
Why?
That doesn't. I should have been consistent, but they're lazy to be consistent. Yeah. So anyway, it's a symbol, right? Yeah. So don't worry if you see a difference like things. So let's say given a discrete state space model, okay, G times X of K and H times U of K, and G at here is n by n matrix, and H at here, let's say it could be multi-input, multi-output, so it could be n by R matrix, so R is the number of input. Okay. Right. Okay. So the definition of controllability is this. Okay. Or maybe I shouldn't call it definition. Let's maybe just call it a sort of objective here. The objective is to bring the state vectors from initial value x of 0 to a certain final value xf here. Okay, certain final value. So you have initial value representing the state vector value x of 0. Okay, and then the objective is basically probably ask is, can you bring this x of 0, right, whatever it starts, okay, to a certain user specified x f of n here. And of course you can't just bring it to there arbitrarily, and you have to bring it by giving the system certain control input, right? So that's why here is by bring this one to here by a selection of u of k here. Okay, right? So it has to be, it's not a selection, maybe not best word, but by giving appropriate control input, okay, into the system. Right? Yeah. So the point here is essentially, I could ask differently, right? Basically, for what type of a control input u of k that you can bring this x of 0 to xf here. That makes sense? Yeah, that's essentially what controllability is, right? Controllability basically means now it's not just one type of final value, right? This is we call it final value. It can be any. It could be, 1, could be 2, could be 3, right? It could be any final value here. Okay? It's a vector, of course. But for any final value, for a certain initial condition, you can always find a certain set of control inputs at here. So whatever you ask for, I'll give you a certain control input, and then I can bring it back from initial value to here, right? Yeah. So that's what controllability basically means. For now, we're not trying to find what this is yet. Okay. So now we're not trying to find. What we're trying to find for this part is under what condition, right? So under what condition that we can select appropriate u, okay, so that x of 0 goes to here. That's basically here. So essentially, what we're trying to do now is to find out this condition here. And that condition is the controllability condition, essentially. Okay? Yeah. So let me stop here. Maybe this is quite straightforward. We'll quickly go over this part in the next lecture. Okay? Yeah. And any questions? It's all good? Excellent.
Is this pretty similar to water control?
Very similar. Yeah. In terms of format, it's the same. Yeah.